Resumen. Hablo en español. I speak in English.
I think it's better for
It's better,
for
man. I
Max.
mean, if you want to understand a bit of Spanish.
No worries, no problem. So this was the discrete Langevin-Monte Carlo process that we are going to. We look about its convergence. Okay, so I have h, which is a time step, and k. Well, h is a time step, and k is the index. So k plus 1 h means the process at time this number, k plus 1 h. And then, so now the thing is, we are going to do convergence via so-called interpolation argument. This is the chapter 4.2 of the book. And then interpolation means that we do this thing. So in the interval from time kh to k plus 1h, we are going to consider here, this is the Brownian part. We put the Brownian part, and then here we interpolate linearly. Instead of, so basically we put, instead of this h, we interpolate from having nothing at having starting, this is the kind of linear interpolation for this part. And the Brownian part, we add we replace the precise time of the Brownian step. And then what to prove is we don't have to read this part, but basically in this part there is this logarithmic Sobolev, some hypothesis. Basically, we are going to see later what is LSI and so on, and we come back to this statement later. But what it says is I look at the kth iterate of this process, and then I compare the equilibrium distribution for Langevin dynamics, and then we look at the distribution of x t for t equal nh, and then the KL divergence is going to be controlled by a term that is minus exponential in L, and then times the KL that we started with, and then plus some other terms that are kind of small, if
So
h is small.
Here mu is the interpolation?
The mu is the law of, mu
law,
t
yeah.
is the law of xt.
Okay.
And then here's the mu at step n when t is equal to nh. So which is the law of this x nh. Yeah, so we proved this. And now we have three ingredients before we start the proof. So here I wrote again the interpolation. And the first thing is saying, well, the law of this interpolation, it has an equation. So this is the equation. Okay? So now it looks complicated. The only way to understand this formula for me was to look at the proof, and then at the end of the proof you understand that the formula is there. We don't need the formula, but we need the consequence of it
But
in the next step.
ignoring maybe this conditional expectation, what you have is this Fokker-Planck equation, right?
Yeah. So you already saw it, but me I didn't see it. So for me it
okay.
was like you don't have to understand it now. Basically, what we start, you have the filtration corresponding to this xkh. So this is like a sigma algebra, and then you do the conditional mu t restricted to this is the conditional probability law. And okay, so. Basically here this is the starting equation that these are satisfying. If you look at the definition of the interpolation, this is the start. This equation just comes from the equation of the Langevin, where I'm putting these conditional probabilities. And then actually this mu t satisfies kind of a martingale property, which in particular, if I take the average the expectation, it gives me this. and so I take the expectation of everything, and here it becomes simpler, the first two terms, and the last term it becomes a little bit more complicated or more simple. It has an expectation in there. Okay, so now I make this square a little bit smaller, and I look at the complicated term. So I look at the part here. Okay, so if I write it out, it becomes this, and then so here mu t times this probability is actually mu t of x times the conditional probability d mu of the conditional probability in d omega. And then so I do this manipulation, and I can take out a mu t of x, and it becomes a kind of expression that depends only on the expectation of gradient v conditional that x of t is equal to x. Okay, so now I plug that in. Here was the previous step, so I plug in the new formula, and then have to remember that the minus exponential of v was actually the law of this equilibrium pi, the equilibrium distribution. And so here I do this manipulation that here it would be like divergence of gradient of mu t, but divergence of gradient I divide and multiply by mu t, and multiply and divide by p. And so in particular I get this term, and then I have using this formula I have another term that I plug in the other part. Okay, so instead of having a Laplacian of mu t plus the divergence of this, I have here divergence of something of mu t times gradient of logarithm mu t over p. And then here I have another term mu t times it would be the expectation of minus gradient of v given xt, but actually minus gradient of t given xt is just minus gradient of v. And so it's summing and subtracting a term between the two pieces. Okay, and so this is actually the same as this thing is the same as what we wanted to obtain. So this, like you say, just the Langevin formula, but for me, you have to look at this. Okay, so basically, here we plugged in the Langevin formula, and we get this expression above. And what we want is this consequence of it, where we are looking at KL divergences. So I would do the KL divergence of mu t with respect to pi, and I look at the derivative of this, because this is going to help later in order to get an exponential convergence. And so this was the KL divergence of something with respect to something else. If mu is absolutely continuous, then you have a formula, otherwise it's infinity. So the formula is that you have the Radon-Nikodym derivative times the logarithm of the Radon-Nikodym derivative integrated against the dp, or you can express it with respect to mu. And then and then I plug that in that formula, right? Let's see. So okay. So basically, so what I do, one takes that formula, and when I do the dt, you can imagine I do the dt of this, where instead of mu I put mu t, and instead of pi I keep pi. And so then what I get, I do like I do normal differentiation, and then in one part I do the partial derivative So like say I use this formula when I have to integrate by parts and I have the partial derivative of mu entering there. So whenever I get the partial derivative of mu, I substitute it by this other part. And so I have here appearing all of this here. This part here is like when I substitute the partial derivative of mu. And then the divergence, so here I have logarithm of d mu over d pi. Here I have this, and this okay. So basically you compute that, you get this formula.
Wait, I just want to have a.
You do a chain rule, so and then you obtain
Yeah,
this formula.
yeah, but the only thing I'm kind of concerned is that okay, you can write the KL in terms of the integral with respect to pi, so it doesn't depend on t, right? So the integral itself.
The pi does.
Then you can let the dt in.
Yeah.
And x log x, you can see it as a function of indirect function of time, right? So if I take derivatives, the derivative enters the integral, then I take the derivative of this x log x, which I guess it would be the first term, the gradient, or that's what I don't see. Like,
so okay, so this part here is the same as here.
yes, but that would come in after using the chain rule, right? So you integrate this x log x, and then you integrate. Take derivatives of d mu d pi, I guess. Yeah, just see it.
I don't, so
Okay.
I didn't do this computation. I believed it. Let's try to do it. Okay, so I have integral of ddt.
Yeah.
And so I have dt. Is that the best? Maybe it's better to use the other formula. No? Maybe
With the mu t?
faster.
Maybe.
And so because it is kind of the same. So I have the integral of logarithm d mu t, so over d pi d delta mu t, and then I have integral of d delta mu t over d pi, and then I have d mu t. I would have over the Radon-Nikodym derivative. And if everything works out, then this should be d pi. No?
Why? I mean, you're taking derivatives of the logarithm, right? So
Yeah.
that's why you get the 1 over mu
Yeah.
t d pi, and how do you derive what's inside?
Inside,
That
the
thing.
chain
How
rule.
do you? Yeah.
Formally I use the chain rule.
Okay, you exchange the derivative of like the Radon-Nikodym derivative with the time
Yeah.
derivative.
I will get, if I'm imagining that these are all smooth functions and so on, then
Okay.
this would work.
Okay. No, that's the part I was not following. But okay, now I get it.
And then here, I mean, if this is d pi, then I have. So this is actually I would get the integral of d delta t mu t.
Yeah.
So this would be 0, canceling. Because the total mass, this would be like the total mass of dt mu t, but if the mu t keeps the mass, then this is actually.
Okay, you pull the derivative, the time derivative back.
Of the integral of mu t.
I see. Yeah.
So that would be 0.
Okay.
And then I get only this part. Okay, so now it's better, no?
Yeah.
Because now I can have the logarithm, and I have logarithm of something of this part times the divergence of this part, and then I move the divergence here, and I get a minus.
Great. Thanks.
No, thank you, because I just believe it. Okay, now in this part, one uses the definition of this number fi of mu given pi, of mu pi. This is like one of the formulas for what they call Fisher information of mu with respect to pi. And so here I observe that I have logarithm, so the norm square of this logarithm, and I take it out, and I keep all the rest. All the rest is inside. Here I have a minus, so it gets flipped in this term. So I just introduced this Fisher information. Yeah, before I didn't explain that here you have Fisher information appearing. So now it appeared the first time, and now one uses Young inequality for the part here that is complicated. And then I have again the square of this, the integral here. This e mu t is like an integral with respect to mu t of this squared, and then I have this other part squared, and then so in the factor in the Young inequality I put 1/4 on this part, and then basically by the martingale property I get this that I remove this condition and I get just bigger. It gets bigger. So I get now if I plug in minus fi and then 1/4 fi gives me minus 3/4, and the other term is the same as in this inequality. So this is the summary of what we got so far. I got this equation that we can forget from now on, and now we have this, and we have to make more understandable what does it mean this, what implication has this equation, but we need this other, sorry, here, I need to massage a little bit this term. So first we look at, we are going to do the massaging in 2 steps. So first we are going to look at a simpler situation when I have the E mu of gradient of V. And then if I apply, if I'm working with the Langevin equation, I have this other re-expression by kind of integration by parts. And then, so what happened in this part? Here, E mu, I can write it as d mu over d pi against d pi, and the E mu of Laplacian of V is controlled by this.
I think beta should be an upper bound on the eigenvalues of, or, no, sorry. I was just thinking it was the Hessian instead. But I mean, what is beta, right? Because beta didn't show up before. So.
Is beta Lipschitz. The Lipschitz constant, yeah, okay.
Okay, so then
it's
it's a trace of the.
Yeah, is the Lipschitz constant of the gradient of V. And so I have the sum of
the sum of the.
I have the Laplacian of f is the sum of delta I of f, where f is the gradient of f. And then so I have d terms. I have here every one of these d terms is smaller or equal than beta. So this is smaller or equal than this, smaller or equal than b times the maximum of DIF, and here I know that the maximum of, so the D is smaller or equal than beta. So every one of these is smaller or equal than beta, so I have smaller than D beta. Assuming, so if I know a Lipschitz condition on the gradient of D, then I get this beta D. And now in this other part, we use something that we saw last time, right? That when when I apply LV of a function against another function, this is actually the same as this Carré-Duchamp polarized version, Carré of FG instead of FF. And so in here is F is equal to V and G is equal to mu over dP. So I get this other part. And now, sorry, what is changing here?
There's a logarithm that appears.
Ah, yes.
What is that?
Right, so instead of having the gradient of logarithm d mu, I have, I mean, if
You start with that.
I start with this, now the next one, I replace the d pi by a d mu,
Ah.
and I plug in this
Same trick,
logarithm, which is basically arithmetics of the what gradient of logarithm is the gradient of what is inside divided by the function. And then the next step is a kind of, again, Young inequality, or like Cauchy-Schwarz maybe inequality, that I replace by the square of one term and the square of this logarithm, of the square of the logarithm, and this square of the logarithm is the Fisher information. Okay, so, and now you see here I have this, and here I have half of this, so I can plug it back on one side, and I get this this bound. So by reordering, the last thing was giving me this kind of bound. This is specific to the to coming from the I think we used something about the Langevin evolution here in this derivation, right? And then so we have this, and the last one is that this red part, logarithmic Sobolev inequality, is implying that the Kullback labeler is controlled by Fisher information, and this we keep it like a black box. Let this red thing, just keep it as a black box, because I want first to use all of this to do the theorem, the main goal, and then we look at the red box. So here is back again the theorem from before, the same statement. So we want a kind of an exponential decay plus error, plus small error, and then what we do, we are going to estimate this dt KL, and we are going to prove a bound of dt KL in terms of KL, and see if you are kind of, I mean, if you are willing to think by yourself, you can forget from, and then take these ingredients, and you are going to not have much trouble to plug that in and get bound by dTKL by itself. Yeah, because if you see, here I have E of square here, and here I can use this to bound it by a Fisher information, and then I have here minus Fisher information, I bound it by minus KL. So I get a bound of KL by itself, and then you could believe it and let's forget about it. But instead, let's not forget about it and do it step by step. And so I start with what I said, with this, that I want to control a little bit and to make it a bit simpler. And so I am stating that this is true. So why does it this is true?
That's also because of the Lipschitzness of the gradient, right?
Ah, okay. Yeah, that's true. This is the Lipschitz constant of the gradient. Yes. Yeah, Lipschitz constant of the gradient, and now this other part is by triangle inequality using the definition of the interpolation there of xt. You just plug it in and use and then you use also the independence that BT, the jumps of BT are independent of this other part, so that it becomes actually equal to the sum of squares. Otherwise, you will get mixed terms also. or just an inequality on some other. And now we are having here we are going to write it out to make appear xt. So we are going to get a bed bound of E of norm of gradient V by this sum of squares times 2, yeah, by basically kind of trying like a version of Cauchy-Schwarz is behind that. And now we can observe that we make appear the same thing as in the left-hand side, and so we reduce to using this blue formula or green formula. I don't see it. So to use it to use a bound for that term for xt. And so yeah, so you have to be careful because this is all multiplied by this quantity. So you cannot, in general, depends on t and h and beta if you can reabsorb it. But here we are putting a condition that h is small enough, and then this can be reabsorbed. Okay, so the time step and t is smaller than the time step. So basically this quantity here, we are looking at t in between kh and kh plus 1. So this quantity here is smaller than h inside the square, the thing inside the square parentheses. So if this is small enough, h is small enough, then I can actually reabsorb it, and I end up with this. So I reabsorb, and the above is equivalent to the one below, where the only thing that changed is that now I have, instead of that term, I have only this term on the right, and then I have a factor of 2 coming out. And now, okay, so two things happened now. Here I replace, I use the fact that it's a Brownian motion, so I know that the jumps have a given variance. So I replace there the variance, explicit number of the variance of a Brownian motion. And here I am using the part in blue, finally, this bound here. Okay? And so also I can get this other bound if I impose something else about h. I can just rewrite it in a nicer way. And forgetting about the factors in front of this fi. Okay? And the nice thing is now I have 1/4. I can make appear 1/4 fi, and so it will cancel with a piece of this minus 3/4 fi. Okay, so I get this in the end. You see here I have this 4 beta squared, 2 beta squared. There is some 6 beta squared, and minus 3/4 and 1/4 is minus 1/2. So I end up with this nice formula, which is almost done. And now I use this black box. I say that, okay, KL is smaller than, suppose that we know that KL is smaller than Fi, so minus 1/2 Fi is smaller than minus 1 over CLS I KL. And then you do the usual thing when you have a differential equation, a differential inequality in one variable. So I put, yes, you see the usual thing, but I don't know what, I never do that. So you are having here, okay, so if you write out this part, then it becomes equivalent to that. If you develop the derivative inside, it becomes equivalent to the part above. But I think there was a more intuitive way to do it in the differential equation course when you find the Grunwald inequality, basically. And then, so now we have this, the derivative is bounded I mean, basically, it was bad that I had this factor, but I can deal with it. I mean, it was bad that I don't have the derivative of something bound by constant, but I can manage that the exponential has derivative bounded by constant, and so I get that my time step decreases with an exponential of h over CLSI every time. And then, so that's how you get that here you get this exponential if you iterate it for n steps. And then here you get these bounds with beta squared n d.
And that those last terms do not depend on capital N?
I mean, if you're, how do you do it in practice? So now I would have that this one is smaller. If I do it one step more, I get that that one is smaller or equal than. I have another exponential, and then I have another one of these of beta.
Ah, but you get the negative exponentials that.
The negative exponential give you a convergence sequence that bounds all the contribution of these terms. Whenever I substitute a formula like all of this, I substitute inside there. It gets every time multiplied by a new exponential.
Right.
So I can remove I keep all the KL part together, and it gives me this. And I get all the sums of exponential. One was this, and the other one was this. I think one of this one, and the other one is this. And you get a CLSI because you get a sum of geometric series. Yeah, I think. Anyway, so and then the theorem had this other part. That case, in particular, I can do I can make a condition of how many steps do I have to continue until it becomes epsilon close to the pi. So if I can use this in practice. Maybe if I put a large enough number of steps, but bounded by this, then I know I cannot do better than that. It arrived close enough to pi, so pi must be around the distribution mu and h. Not too different than mu and h for this large n. And so now the main goal is to understand what is behind here, that we use the when does the KL get controlled by the Fisher information. So basically hidden in here was that here I have a KL. Here I have this Fisher information quantity, which is has gradients inside, and the KL that doesn't have gradients inside. So in a way, I have a bound by I can this inequality written here says that I can bound an object without gradients by an object with gradients and logarithms, mixed in gradients and logarithms. And so it's like Sobolev inequality, but a version with logarithms, right? That's why maybe it should be related to logarithmic Sobolev inequality. And so, and this content comes from a previous chapter of the same book, yeah? And so again, KL is this, and let me just slowly, like a spoiler, then we get to Log-Sobolev inequality in general. What is the definition for a Markov process, okay? And so basically what we are doing, reminder the KL inequality, and now you suppose that you have a density of PT over P. So if I have an underlying probability, that would be the equilibrium probability for a Markov process, and the PT is the time t probability of a Markov process in continuous time. And this would be the infinitesimal generator. So that would be we're setting us in the case where you have a nice infinitesimal generator for a Markov process. And okay, then this is if I write the KL in this case, then I can simplify here. dpt over dp over p is equal to rho. So I get rho log rho against the ambient, the background probability p, and you can make appear the L. You can use the equation here, and you get this. And actually, this is defined to be like the energy, kind of a minus energy associated to your Markov process. which is the same that we saw last time, this kind of energies that we saw last time. And then in that case, this is what they define to be the Log-Sobolev inequality for a Markov process. You say that that it satisfies for all. Basically, it doesn't matter what is ended up to be rho t, because in fact rho t depends on rho 0, that you would do like you do the starting point like you want, and then you apply the Markov process, which gives this equation. And then they ask for all probability, all densities, that you always have this kind of bound. So again, like a function is bounded by things involving gradient of the function in a way. I mean, the gradient is not there, but is like there is this L, which is should be somehow reminiscent of a Laplacian. So then this would be somehow reminiscent of gradient square of something. That's why it's called Sobolev, because there is a gradient hidden here. It's like a gradient square generalization of, but with logarithms.
So what I find confusing though is that the KL divergence you're measuring for rho pi, which is
rho is a function here, supposed to be a function.
Is a density.
Yeah.
But
the
rho is
Radon-Nikodym derivative, you can think of rho.
Yeah, I see. So these are two probability distributions then.
Yeah.
Okay.
Is a Radon-Nikodym derivative of pt with respect to p, but also of another mu respect to. So you can, instead of saying mu, here they say mu pi, because
Right.
if you don't, it doesn't want to care about the case that you have mu's that are not absolutely continuous with respect to pi. The universe space for this thing is the measures absolutely continuous with respect to pi, to the equilibrium distribution.
Yeah.
And then this is not in order to prove. We are not going to prove this, but it is not very. To me, it seemed like when I read it, I remember it seemed reasonable. So what does it say? It says it's equivalent that we have a Log-Sobolev inequality, or that KL is decaying exponentially. I mean, this seems reasonable because we have dt KL is bounded by E, and if E is minus E, and minus E is bounded by KL, like a little bit simplified version of what we already did, you get that this is bounded by itself, by minus itself, and then you get an exponential decay like before, with this inserting these exponentials and finding that that you get the kind of Gromwall inequality. Okay, so that's what they say in this chapter 1.2. And then then they say this, which are going to enter. Now we are entering into more detail, because this is what our second main goal for today was this, that you say that if Langevin diffusion you satisfy this condition, then you get KL is bounded by the Fisher information. So this is actually what we wanted. Here, this is like the Fisher information. One of these formulas is equivalent to Fisher information. Okay, so this is the same. I just changed size of the thing, and so here it was. Actually, maybe I wasn't completely here when we saw this, and maybe somebody did it before in the last lectures, but that was how you get that the Langevin diffusion has this generator. Yeah. So let's take this for granted. For the Langevin diffusion, the generator is like a Laplacian with a gradient of V next order. I mean, the degree 1 part is the minus gradient of V. And then this is what we saw last time. If we have a more general hypothesis that we have a Markov's reversible Markov semigroup, and I want to calculate F minus generator G against dP, where P is the equilibrium distribution, then I can integrate the Carré-Duchamp, and then this is actually the definition a little bit of the energy here. And energy functional is like, so if you have a quadratic form, you can always polarize it and look at the one that has two different entries. Instead of looking xtmx, you look at ytmx for a quadratic form m. And so this would be the polarization of the energy, which is given by well, I think it's nice to have to remember this formula because it's what appears here, hidden in here, and then we can use the precise formula for the Langevin, and like we saw last time, in the end you get gradient f, gradient g. So when I want to write this out, this formula for the energy, I end up having a gradient of mu over t logarithm of mu over t, which is and when I integrate this against pi, is the same as integrating 2 times the gradient of the logarithm against mu. And so I get really this Fisher information, right? So in the end, this is why you get this red part, which can be also abbreviated like this red part that we used before. Okay, so this was this concludes in a way the proof of the theorem. And now, but I don't know. For me, it seemed like, so when does LSI hold? So this seems like yeah, we are using it, but so when can we use it? And so the theorem 2, the section 1.2 keeps talking about this, and it says, it talks, this is the Beckery-Emery theory, I guess, or this is one of the examples of Beckery-Emery work. So they are doing diffusion Markov semigroup. If I have a Markov semigroup like before with a generator, then they have this curvature dimension condition, which is telling you that the space is a little bit curved in a way. We are going to see it later. Then Log-Sobolev inequality holds, okay? And the constant of the Log-Sobolev is given by this alpha in the curvature dimension condition. So this is like, it doesn't say if and only if, it says then it holds. So it's a stronger condition than the CLSI, this curvature dimension condition. But this is the only other property that allows to know that LSI holds. And so here the curvature dimension condition is this thing. So here you have, like in Riemannian geometry, when you have I have a metric, and then I look at the Christoffel symbol, then the Christoffel symbol have this expression of the metric, where here you have derivatives. So this is like a version of the, I think it's like, it's based on the Ricci curvature. I think because here is like double derivatives, not a single derivative. So anyway, this is like a curvature in the space of measures where there is a correct way to interpret this curvature. And so they say that the curvature, which again has derivatives, applied, is bounded by below by the Carré Duchamp itself. So this is the condition, and then in that case you get Log-Sobolev inequality. Okay, so it's still another condition where you have a gradient bounded by the function, gradient square, in a version of gradient square bounded by alpha times the function. Well, then I get, for the logarithmic version, I also get the same kind of Sobolev inequality. So there is a curvature interpretation on the space of measures with this generator of the semigroup has a curvature condition if you can do this bound. And then the curvature condition for Langevin, it says that it holds if and only if the potential is strongly convex. That is the second partial second derivative matrix is in the sense of positive definite matrices is larger than alpha times the identity. So this is the condition. A strong convexity condition implies logarithmic Sobolev inequality, right? So this is the possibility if you know properties of V. but actually logarithmic Sobolev inequality might be weaker. I don't know an example, but it doesn't exclude that. And the other thing that they say in the book, they say in this chapter 1.2, all the different kind of conditions that are looking like curvature condition or a logarithmic Sobolev inequality. So there is this one that we saw, that the alpha strong strong convexity of V, or log concavity of pi, which is exponential of minus V. So this is giving the logarithmic Sobolev inequality. Or there is conditions that are called T. T is for Talagrand, and the number depends on the type of Wasserstein distance that one considers. So W2 or W1. And I don't know if I wrote any of this. No, that was not. That was my last slide. So there are some conditions that LSI is like also weaker than conditions on kind of some kind of convexity condition for the generator of the semigroup of Langevin evolution in Wasserstein space. So in Wasserstein 1 distance, on Wasserstein 2 distance, and then there is the usual Poincaré inequality that is incomparable. So here it says, so we have this log concavity implies LSI, LSI implies T2. So T2 is weaker, and okay, so T2 or T1 should be the strongest conditions, right? And then T2 and T1 are kind of comparable. T2 implies Pi, and the Poincaré inequality, and the LSI then implies the Poincaré inequality, but the Poincaré inequality and the other version, that is T1, doesn't hold. Okay, so there are many convexity conditions that you could try, and a weak one seems to be Poincaré inequality, and the second one is this curvature condition for Wasserstein distances. This is the other chapter. I think Nicolas is going to talk about this Wasserstein interpretation. But again, the only criterion that you often, also in the other case, in the spoiler for the future, always you get a condition like this. Sorry for the. So you get a condition like this, that you have the way to the simple statements that you get are that your potential should be strongly convex in a sense, and then you get your the inequality that allows them to get the exponential convergence. And they are always, there is always like that there is a curvature on your space induced that this operator is like convex, or you have a curvature condition. These are the formulations. You can geometrically you think of convexity or curvature bound. Yeah. So that's it.
Nice. I was going to say about this result that, I mean, I guess it's important for it that you're working on the whole space RD, right? Because, for instance, if you have a manifold, there are other conditions that imply, even when you have a potential, like if you have a space with positive curvature, the uniform distribution will satisfy the curvature dimension condition. But the potential itself doesn't have it. Well, I mean, it gets tricky. All that I'm saying, like, if you're working in like unconstrained Euclidean space, yeah, you have an if only if. But particularly on manifolds, it seems that this is like a more nuanced property.
Okay, so if you have a manifold,
I mean, there's a different way to define everything, right? So the Carré-Duchamp.
But like a manifold, like what manifold, for example? I don't know. What do you think?
The sphere, for instance,
okay.
in
so
d
you
dimensions.
have an evolution on the sphere.
Right.
And then?
Like you have Brownian motion, say, like a constraint on the sphere. Then you would have a Carré-Duchamp operator, so you can define everything, right?
Like a Markov semigroup, yeah,
yes,
of course.
yes.
Markov semigroup.
And then there's a notion of curvature dimension there.
Yeah, I think this, I know more than the Wasserstein, and I think it implies a condition on the curvature of Wasserstein space.
Ah,
Also, the curvature on the manifold, if it's bounded uniformly across the manifold, it implies a condition of the. So this is the work of Otto, Sturm, and Bilani. That you kind of get also there. It works for manifolds as well. This is the one that I know.
Okay.
That you have a condition on the curvature of the manifold, and the space of probability measures is curved as well.
Uh-huh.
I don't know if this sounds like you're saying, but I don't know.
It's similar. It's similar. So, for instance, I think that I mean I don't know this by heart, but in the case of, for instance, on manifolds, this curvature dimension would be related, for instance, to the Ricci curvature for the uniform distribution
So
set.
the Ricci usually is Ricci.
Yeah.
Because the Ricci is giving or there are some others, but the simplest one is the Ricci condition. There might be these other ones that no, but I think it's mainly the Ricci, or then there are this Matt-Rudinger-Wang bounds, but I don't know how they work.
Okay.
And they imply the Ricci, but they are like more precise. But I never entered into the theory. But for optimal transport curvature is usually the Ricci bound implies that the geodesics are in a way convex for the Wasserstein, and from there on you can try to use it. I don't know the details.
Nice. Okay.
Okay. I can, if you want, I can.